Okay. Ladies and gentlemen, recording has started. So, first, as far as the quiz from Friday that I gave you to take home over the weekend, graded it, that quiz was the last grade on your third quarter grade. Grades are updated. Grades were updated last night. I rounded them if necessary. So what you see right now is pretty much what you get. If you got something you need to talk to me about, let me know. Discuss. I can shoot you down. Anyway, check it out. Let's see what you got. Then, on the quiz from the weekend, there were two questions that I wanted to discuss with you because if people miss points, that's where they miss their points. And those two questions were number 4 and number 5. And grab this. And there they are. So, two things I wanted to discuss. First, this quiz being about work and work energy theorem. The first question on your quiz talks to you about how do we calculate the amount of work done on an object. And in order to calculate the amount of work done on an object, we need to know two things, right? We need to know what's. In order to calculate the amount of work done on an object, force and distance, or displacement. Okay? But our definition of work can also allow us to figure out how much work is done. What was our definition of work? Transfer of energy, which means that in order for work to be done, you did go to that. Anyway, in order for work to be done, there has to be a change in energy. So, we go here to this picture. First, it tells you there are 3 cars. They're all traveling at different speeds. Most of you could probably figure out which one was traveling the slowest and which one was traveling the fastest. It says that they slam on their brakes. The force applied to the cars is exactly the same in each situation. Based on that, answer the next 2 questions. So, let's go here. If we talk about work energy theorem, we've discussed the idea that the amount of work that we do is equal to the change in mechanical energy. We also said we could rearrange this equation to look something like this. MEI plus work equals MEF. If we look at this situation specifically, regardless of what the actual speed was at the beginning, what kind of energy would these cars have at the beginning of this situation? Kinetic, because they're moving. If we call the ground the reference point, we can pretty much get rid of the potential energy by saying that they're at the reference point. There's nothing stretched or compressed. There's no elastic. So these cars are going to start off with kinetic energy. Then there's some work done. And as a result of that work, right, first, what force is being applied to these cars? Pretty much friction. Friction goes which way compared to the motion? Opposite. So what kind of work does friction do? Negative work. Reducing the amount of mechanical energy that these objects have. What eventually has to happen at the end of these situations? The object has to stop. With that being said, does it have any kinetic energy at the end of the situation? No. No potential, because it's still at the reference point. Nothing stretched or compressed. So what would be the right-hand side of this equation? We know that the work is negative, right? So we can kind of make this like a negative W here. And that means that KEI has to equal the amount of work that we do. We already discussed work depends on 2 things. What are those 2 things? Force and distance. You got force here, you got distance over here. We can kind of substitute that in there, right? Or displacement, concept was. Kinetic energy, we said, depends on 2 things as well, right? What are the 2 things? mass and velocity, right? But the one thing that is important to this problem, what are we doing to the velocity in that formula? We're squaring it. This equation right here is pretty much how you're going to figure out this problem. Okay? So if we go to problem number 4, okay? It says, what was the speed of the car before skidding 40 meters? So that would be the C referenced here. What do you see about the distance from the first skid to the second skid? It's longer. You're going how much longer? 30, but if we talk about it in terms of factors, how many times longer is it? 4. It's 4 times longer. So the distance is 4 times longer. Right? What did we tell you about the force in the problem? It's the same. 3 cars, I probably should tell you here that the cars all have the same mass. Probably should know that. Anyway. Yeah, whatever. Okay. So, with that being the case, if one of you brought it up, then maybe
I was thinking that.
Yeah, I'm sure.
Didn't have to.
I'm sure. If the mass is the same, right? T goes up to a factor from 1 to 4, right? But what does that mean from a velocity standpoint? The velocity is twice as big because 2 squared gives you 4. So that means that the answer to this question is 60 kilometers per hour. Okay. The next one's a little bit trickier. Spring. For part 5, or for number 5, it says skidding distance of the car that was traveling at 120. Right? How much faster is that car going than the first car? 30 to 120?
Where's? Oh, 30. I was looking at 40.
No, 30.
You're still looking at the difference.
Yeah, so it's 4 times bigger, right? So this one, 4 times bigger than this one. If we take it back to our equation, right, that 4 influences this factor right here. But what are we doing to that factor? Squaring it. So 4 squared means what? 16. Here, 10 meters originally, right? But if you increase the speed to 4 times its amount, the stopping distance that it requires, 16 times that amount. That makes sense? Now you're looking at the relationship between the amount of work that you do and the change in the energy. In the case of kinetic energy, that speed is a squared factor, influencing how much change in energy. Good there? Instead of just calculating force times distance, now you have to look at what change in energy is occurring to get to that. Questions? Everything else pretty much everybody did well on. So if you have questions about number 1 specifically. Yes, ma'am. Okay. So Manny, for number 4, okay, here we know that the distance is 4 times bigger. So that's going to influence this side of the equation, and specifically that distance value. Okay? From going from the first car to the second car. No. She has tap shoes on.
Do it. Come on, yes, you do it. Oh, do the arm.
All right. Glad we got that under control. All right. So, back to our question. Here. So, in this case, the distance is going up by a factor of 4, which means this side of the equation is 4 times bigger. That means that the kinetic energy side also has to be 4 times bigger to make it equal. The mass doesn't change. That means that the velocity has to make up for the difference. But what are we doing to the velocity? So to make it something that's 4 times bigger, you only need twice as much velocity because you're squaring the velocity. That makes sense? That's where we go from 30 to 60. Questions? Next. Yesterday, we discussed the idea of conservation of energy. And before we discuss the idea of conservation of mechanical energy, okay, let's go here. We discussed the idea of a conservative force. First, there are two conservative forces out there. What are the two conservative forces that we discussed yesterday? Gravity is one, and then springy, elasticy forces are the other one. Okay? But more importantly than what conservative forces are, I had to put the or like my first grader, we were supposed to do this when he spells something wrong. We're supposed to circle it and above write the correct spelling like that. There you go. So, by the way, he can spell spring, I'm pretty sure. Anyway, there's our two conservative forces. But we said more importantly than what conservative forces are is what they do or what they don't do. We said that what do conservative forces do or what don't they do? They don't change the amount of mechanical energy, but they will convert one form of energy into something else. And that leads us to the idea that if you start off with a certain amount of mechanical energy, you are going to end up with that same exact amount of mechanical energy. And as we discussed previously on several occasions, mechanical energy, right, is actually a combination of three things. Okay? Those three things are kinetic, elastic potential, gravitational potential. So over here, on each side of this equation, this is a sum. And that formula ends up on the wall. Good there? All right, with that being said, let's go here. This is a problem for your book. It's the end of chapter 10, maybe 11. I can't remember. All right, it says, physics book of unknown mass has dropped 4.50 meters. What speed does the book have just before it hits the ground? So, if we neglect air resistance, from the time it leaves my hands to the time it hits the ground, what's the only force acting on it? Gravity, right? Gravity being a conservative force means that we can start off this problem like this. How do I know it's going to be this kind of a problem instead of the work energy theorem, which we did last week? Things like neglecting air resistance. If I'm on a frictionless surface, okay, where we're taking out all those other forces so that gravity is really the only thing. It could be a springy force. Hopefully we'll get to that later. We'll see what we think. That's telling you, hey, this is going to start off as a conservation problem as opposed to a work energy theorem problem. But, like we said, these two sides of the equation are sums. They consist of the combination of three things. So, before I drop this book, or right when I drop this book, okay, what is it doing? Is it moving? Right when I drop it. Just like when we did a kinetic equation problem, right? Right when I drop that ball or marble or whatever it is it moving the instant after I drop it? It's not. So there's no kinetic energy at the beginning. Is there potential energy? Probably if we call what our reference point. If we call the ground our reference point, right? If we go, this is our picture here, right? Book, right? If we call this our reference point, which makes the most sense in this problem, then there will be no kinetic energy at the beginning of this problem, but there will be gravitational potential energy. So we modify the right-hand side or left-hand side of this equation to look like this: PGI, or the initial gravitational potential energy. Is there anything being stretched or compressed in this problem? There's not. So no elastic potential energy. On to the other side. Book starts off at rest, but then it falls, and we know that as it falls, what is it doing? It's accelerating, so it's going faster and faster and faster. And the moment right before it hits the ground, right, what can we say about its speed at that point in time? It's the fastest it's ever going to be. Those are all old concepts. But from an energy standpoint, right, now, what is it doing that it wasn't doing at the beginning? Moving, so it has what kind of energy at the end? It has some kinetic energy at the end. Okay? So there's some final kinetic energy. Okay? But now, where is that object located right before it hits the ground? If we talk about that very, very instant, like right before it hits the ground, right? What height is it at? Exact height 0. So it doesn't have any potential energy at that point in time. Gravitation. It does not. Does it have any elastic potential energy? Nothing's just compressed. So this is what our problem turns into. We have actually probably done this before. Yesterday was pretty much like this problem. But the one thing that makes this problem different, here, formula for gravitational potential energy. Gravitational potential energy depends on 3 things. Depends on the mass of the object, the acceleration of gravity, and the height from the reference point. On the other side, we just discussed earlier, kinetic energy depends on 2 things, right? It depends on the mass of the object and its velocity. All right, so start plugging in things we know. So we don't know something, right? We don't know the mass. Is that a problem here? In this problem, specifically, is mass in every term of this equation? It is. So what can we do mathematically with it? If we divide by the mass, right, this goes away and this goes away. Now, something you have to keep in mind. We are only allowed to do that if mass appears in every term of this equation. Okay? If elastic potential energy gets put into this somehow, remember, here's our formula for elastic potential energy. Okay? Mass does not appear anywhere in that formula. So if elastic potential energy shows up, or if it's a work energy theorem problem where mass doesn't show up in the formula for work, you can't do this. It's got to be in every term of the equation. The math thing, but you can make mistakes all the time. Okay. So now, do we know the acceleration of gravity? What can we do by now? Do we know the initial height of that object, where it starts? Right? That would be 4.50 meters. Then the only unknown we have in this problem is the velocity. I guess we should probably call it the speed. No. So, good. Yes, good question. So Ellie asked, is gravity negative in this problem? And we said that no, because what does the negative on 9.81 tell you? It tells you direction. But we said that energy in general is what kind of a quantity? Energy is scalar. So the negative on the 9.81 doesn't come into play here. All it is just the acceleration, or the magnitude of the acceleration. Why in that formula that could be different? But in this case, we won't worry about it. All right, good there? All right, next. Justin. Justin throws a 10-gram ball straight down from a height of 2 meters. The ball strikes the floor at a speed of 7.5 meters per second. What was the initial speed of the ball? So, we're looking for this, right? Things we know. Know the mass of the object. It tells us that it's 10 grams, but we don't want it in grams, right? We want kilograms, so I'm just going to do that right away. Displacement does not show up here.
For height.
Okay, so we know the heights. That's going to be the initial height, as long as we do what? Because that height depends on what? The reference point, right? So anywhere we put a reference point. Yeah, so basically we're probably going to call the floor the reference point. All right, what else? Okay, we know the final velocity. Speaking with the final velocity. Okay, 7.5 meters per second. Okay. But what are we looking for? We already decided we were looking for the initial. All right, we good there? So, quick picture, right? Ground, level, ground, ball. The one thing that makes this problem different is that when it starts, what is it doing? It's already moving, right? We've already established the idea, running through our discussion, that we're going to call this our reference point. But if we neglect air resistance, which it should tell you the problem, but it doesn't, but let's assume we are. If we neglect air resistance, from the time Justin throws it to the point just before it hits the ground, what's the only force acting on it? Gravity. That means this is going to be a conservation problem. Here's where this problem gets a little different. Let's take a look at the beginning. Is the ball at the reference point at the beginning of this problem? It's not. So that means it's going to have what kind of energy at the beginning? Definitely gravitational potential. But, as we just discussed, what is it doing right when it leaves Justin's hand? Yes, but more importantly, from an energy standpoint, it's what? It's already moving. So that means at the beginning of this problem, it has gravitational potential energy because it's not at the reference point. But what else will it have? It will also have kinetic energy. On the very first day, we discussed, on the very first day doing energy stuff, we discussed it can have gravitational potential and kinetic energy at the same time if it's moving and it's not at the reference point. Nothing stretched or compressed, so we have no elastic energy. But then, over on the right-hand side, okay, where does it end up? We do this, right? It ends up where? Pretty much at the reference point, right? So does it have any potential gravitational energy at the end of this problem? It does not. But what is it still doing at the end of this problem? Still moving. So that means that now it still has kinetic energy. Does that make sense? So we can have two different forms of energy at the same time. Right? Remember that in this equation, right, the two sides of that equation are actually sums, right? The sum of the kinetic plus the gravitational potential plus the elastic potential. So we have to look at our problem and say, okay, what do we have here? What do we have here? Now it's just a matter of plugging in things we know, right? Formula for gravitational potential, mgy, where in this case we want the initial height because we're talking about the initial gravitational potential, plus formula for kinetic energy, 1/2 mv squared. But in this case specifically, we want our initial velocity because it's the initial kinetic energy. And then over here, one half mv squared again, but now we want that final velocity. Good there? Mathematically, what can we do as our first step here? Okay. We can cancel the m's in this case because it does appear in every term of that equation. If it's not in every term, you can't do that. It's got to be in every term. Now, do we know g? We do. Do we know the initial height? We do. We don't know the initial velocity, but that's okay because that's what we're looking for, right? And then they gave us the final velocity in the problem. We've got everything we need to solve this. Just turn my name.
That is weird how it works. It's weird how it only works in shape.
Magic. Definitely witchcraft. All right, so we good there?
Really?
No, wait, hold on a second. Wait. So, for homework tonight, the problem set that I gave you yesterday, the answers are all posted for all those problems. The ones at the beginning are a little easier, the ones towards the end are harder. Okay? I want to do one more example problem for you tomorrow before we get into lab, so that we'll be at the beginning of our class tomorrow. All right, good job.
I don't get out.